All right, Jillian, tell me one of these reduction potentials.
Silver is
Volts, right? Okay. Drew, tell me the other one.
Iron 0.77 volts.
And so we're clear, like this is iron 2 and iron 3. Everybody's good? 0.7, what was it?
771.
771 volts, okay? So this is the standard reduction potential for both of these reactions. So if we're making it galvanic, we want this reaction to occur on its own, so we want it to have a favorable forward direction. So which of these would be willing to give up electrons more? Silver, right? The higher the reduction potential, the more likely it is to give, not give up electrons. I meant which was more likely to be reduced, the one that's more likely to gain electrons. So this one has to be Rig, meaning it has to be the one that's reduced. And is this the correct half reaction for a reduced reaction? First you meant? Yeah, it's gaining electrons. We're good here, okay? So then this has to be the oxidized reaction. Now this is not how we should write it, but remember we are always given half reactions as reduction, especially since we're using the reduction potential list. Therefore we have to now decide who's the anode, who's the cathode. Who's the cathode? Silver has to be the cathode, and then who has to be the anode? Iron what? Technically. Iron 2 technically has to be giving up electrons to make iron 3. So it's actually a flipped version of this. But we know that overall these are the ions in the anode compartment. So I'm going to draw it backwards then from what you guys probably started. So I'm going to put my anode over here and cathode over here. So who goes in the anode chamber? Iron what? 3 plus and iron 2 plus, because neither of those can be on the electrode itself. So who has to be the electrode here? Platinum. I'm going to go carbon just because you guys said platinum. So platinum or graphite, whichever one should work. And then we're going to have our external wire. How are electrons flowing? From the anode to the cathode. So from right to left. Okay. And then who is the cathode electrode? Silver solid, right? So we do have a solid here to work with. And then who's in the cathode chamber? Silver ion. And then what's happening to the mass of the cathode electrode? It's what? It's gaining electrons, which means that the silver ion precipitates on itself, on the silver itself. So it makes like a little beard, but don't say beard ever on my FRQs or on the AP exam. Sometimes we say things to help us remember it, but it's just increasing in mass. And then what's happening to the, well, actually, what's happening to the carbon electrode? It's remaining unchanged. Itself is not involved in redox. It's just a conductor that will help the electrons move through the circuit. So there is no change to the carbon because itself is not part of the redox. These will change in concentration, one way or the other, but there's no change in the mass. Okay? There would also be a color change because iron 2 is a different color than 3. Yeah.
If you flip the equation, change its sign.
No, don't say change any signs. Point blank.
You shouldn't even flip the equation.
If I'm going to write this reaction now, but I wanted to draw this first. Yeah, so you will have to flip this equation to show the full redox reaction, but do not change these because then we'll have there are 2 ways to calculate ECL. I'm teaching you one so you never can mess it up. Okay, so do not flip these. Okay, you might read that you can flip them because there is another way, but try not to because I don't want you to mess up your method here. There's one thing missing from this. What is it? Salt bridge. So what ion is going to move towards the cathode? Right, the cation will move towards the cathode because it's going to neutralize the negative charge that's beginning to build up as these electrons get deposited. And then what ion moves towards the anode? The anion. And that's going to happen because as there's a loss of electrons, it becomes a positive overall charge buildup, so we want to neutralize that. So our battery continues. So speaking of our battery, how good is our battery? Not very, okay. So E cell is equal to E what? E what? Red, right? So the half reaction that is the reduced one, minus the E ox, which is the half reaction, which is the oxidized one. So that's what minus what? Who's the reduced? So that's silver, so that's 0.79 volts. And then iron is the oxidized one, so minus 0.771. What do we get? Point what? 02 or 019? Yes? Okay. Crappy battery, but it's there. So E cell, again, is positive for galvanics. That's the one thing you should know. It's a negative delta G means spontaneous forward direction, thermodynamically favorable, but a positive E cell. All right, so then for this reaction, I want to know the overall electrons transported or transferred. That was a question on your 1 through 9. So we have silver ion, 1 electron yielding silver solid. What was the half reaction for the iron one? Iron 2, right? Yields iron 3 plus 1 electron. Hey, there's only 1 electron transferred from the loss and the gain, so we're good, we're balanced out. There's 1 mole of electrons transferred. That's it. If there were a multiplier, let's say it was like 2 and 3, the least common multiple between that would be 6, so therefore there would be a net of 6 moles of electrons transferred. So this would just be silver ion plus iron 2 yields iron 3 plus silver solid. And that would be our overall reaction that this cell is describing and that this E cell value is describing. Cool? What's the cell notation or the line notation? So how do we always start? The solid electrode, if we have, well, the solid electrode here, we will always have a solid electrode. So start me off. Here's the anode. See, I drew it backwards so you couldn't just go with the flow. You gotta like critically think of what you're doing here. So who is the anode? Carbon, and then line, and then who's the anode chamber? Fe2 plus Fe3 plus, just kind of just a little comma between them. And then double line for salt bridge, and then silver ion, and then silver electrode. Okay, so watch that so that you're able to, write down who's anode, who's cathode, like up front, so you don't forget that. Okay, so one more thing on from yesterday, I didn't get to go over what a volt was, just a little bit more in depth, and then we're gonna do our lab. Okay, so write down. Not this yet. We're gonna get to this soon. So write down 1 volt is equal to 1 joule of work per coulomb of charge transferred. 1 volt is equal to 1 coulomb of work. 1 joule of work per coulomb of charge transferred. So if you would explain what a volt was in your own words. Now, what you got?
It's like how much actual,
You're good. How much actual?
Like, can I say force? Like, gets, like, made per how many electrons are transferred across.
Okay. So how much force or how much work can be done by this battery?
Yeah.
So if there's a large transfer of electrons, you have a lot of charge. A lot of charge can do a lot of work. And so, yeah, so you're talking about pushing electrons and how the force can help create a larger amount of work. So we should know that 1 volt is equal to a joule coulomb. 1 volt is equal to a joule coulomb. And that, like, rearrangement of those variables, so like joules, so what does a joule equal? A coulomb volt, right? So 1 joule is equal to a coulomb volt. We'll be rearranging these variables in some way after a break. But today we're looking at volts and only volts. And eventually we will talk about Faraday, which is Faraday's constant, which talks about charge based on the number of electrons that are transferred in a reaction. Okay? All right, microvoltaic lab, ready? If you have your lab notebook out, you can just add these couple of details. But I just want to make sure you know what you're doing here. So, pretty easy lab. You have 5 unknown metals, yes? 5 unknown metals. Your job is to identify those metals based on their reduction potential. So, you'll be measuring voltages, determining their individual metal reduction potentials, And then how would you match those, or what would you look at to kind of match the reduction potentials? Your big O chart, right? So look at the chart to see who's got what reduction potential, and then you can match that to the metal that you think it is. Of course, you guys have a plethora of knowledge of like what metals look like. You know, I can kind of guess what the metals are, but you have data to support your hypothesis. Your data has to support that. So basically, you have to choose the metal that's closest to the reduction potential that your lab decides. Now, you also can be hesitant, like, I think it's mercury. I'm probably not going to give you mercury, right? So you're going to think it like, you know, logically as well. Okay, so the cathode, remember, I'm telling you first of all, like, just a little bit of background if you want to write this down for yourself, and then how we need to like work the electrodes here. So the cathode is the positive electrode, the anode is the negative electrode, and that's from the perspective of the voltmeter. Remember, the voltmeter is at the top of the circuit, so it sees electrons coming from who? From the anode, so it looks like that's the negative. And then the voltmeter sees electrons going towards the cathode, which opposites attract, right? So it looks as if the cathode is positive. So that's just sometimes how the labels are written instead of anode, cathode, it's written as positive, negative. And so that's just based on the perspective of the voltmeter, so you can see how the electrons are traveling. And then to make all these galvanic, we can't have a negative E cell. So when you test, basically you're testing a red alligator clip and a black alligator clip, that you're touching two different metals. If that's negative, just like in the simulation yesterday, you know, you were like testing voltages, if that's negative, that means that your clips are in the wrong place, so you flip them. So if you ever get a negative E cell or voltage, you need to flip your leads, which will mean that you now know who's positive, you now know who's negative, and that's going to be recorded as the anode or the cathode. Okay, so in this blue part here, it tells you which is which. So you need to record who's the cathode. The cathode is the red clip. You need to record who's the anode, which is the black clip. Okay, so the positive reading means the red clip is higher in potential, which we now know higher potential means what? A higher reduction potential means what? More likely to be reduced, meaning you're the what? You're the cathode, right? You were the one reduced. So that's basically how you can read what your little leads are telling you about. And before the lab begins, before you start touching metals, you have to take your two, like your red and your black electrodes or your alligator clips, and you have to touch them to zero them out. It's not going to shock you, okay? Just touch them and zero it out. It's kind of how you calibrate it. Some of our samples are kind of Enlo made them, so just if they're weird or off, it's because I have no access to those materials, and so alchemy kicks in and I have to make them. Dropper bottles I have them kind of lined up on the side. Just take what you need for the moment. I do have mostly like 4 or 5 of every bottle, but there's going to be 7 groups, so just share. And then in terms of making your salt bridge, you need to have like a controlled, oh sorry, not for salt bridge. Basically, you guys saw the little diagram. It's like a little star shape. Yeah, you're going to cut your unfiltered paper to size. You're going to put a drop of metal 1 through 5 solutions, and you're going to put your little piece of metal on top of that. And that's going to be your cell, like it's like an aqueous solution with the metal piece on top. And those metal pieces are what you're touching your alligator clips to. But there's no salt bridge, right? So you have to actually take a sodium nitrate solution, and you have to drop a salt bridge so that the salt bridge touches each combination. But it's not just a mess in there, because if you have a mess in there, your salt bridge will start to make this connect to this when you're trying to connect this to this. So keep it clean. Yeah, and then the optional part's not optional. You have to identify the metals. At the end, it says like to dispose. Don't dispose of everything. I'll get the metals back. Make sure you wash them off before you give them to me. We'll put them back where they belong. Okay, it's pretty easy. All right, ready? So groups, 7 groups. So it's groups of 3. Okay. Groups of 3. Right. How many? You got an internal manager for your group? Grab.
Guys, like, I got more than 7 groups. No, we have 7 groups. Groups of 7 filled out. Two rows. Okay, then go to another group. I thought I had 3 people missing. So, another group. Great. Alright, so your tables, then you sense that you have a lot of rows. Your link. Your link gets plugged in. The goal here gets plugged into your link.
So we got to do this. Yeah.
We ran on the same normal sound, or is that gonna be?
Excuse me?
We draw on.
Yes, you'll put, you guys see the count, like,
It's going to draw off more. It's in the draw
if you're using pencil, pencil has graphite in it, graphite is conductive, it could affect your results. No, don't do your analysis, fix it. I'm telling you right now, do not use pencil. Alright, so I need everybody to need one person to come and get samples for your filter paper. So you're getting metal samples now. Make sure you There's wine, go ahead and grab wine. Your fingers will make like little oil drops or oil in some areas you don't do it. That's one grab and one. Grab your hand. You guys keep that one. Okay. And so this one's got like a little crud on it. So that's why I would use your everyday You're in steel wool. There are baby pieces and big pieces, so just do it over the trash cans. You don't get like conductive steel all over your table.
She's not really, she's harder. No, I'm talking about this one.
I steel wool. Everybody got steel wool. Alright, I'm closing up the middle one. Alright, somebody else can start to grab the M1 through M5 solutions. You need to take a bottle, bring it to your station, bring it back. I only have 4 or 2 of each line. You're not grab one each. Grab one at a time, bring it to your station, bring it back. I only have 1 through 5, right here.
Get that and put it on the surface. Always take place at near so you can keep track of which one's what.
Alright, Alright, once you get M4 on there, raise your hand and I will bring you M4 metal. Once you get M4 liquid on there, raise your hand and I'll bring you M4 metal.
We need to put 3 drops on this on compressor.
Isn't you already
Alright, when you get M4 drops on your M4 supply, pop up. It's just practice.
What am I doing wrong?
The only thing we need to
I'm trying to apply my messages. Oh my word. This isn't working. Hey, look at that. I gotta go. Yeah, what's it? 3 drops. Whatever drop.
Alright, I am coming to somebody's M4. Thank you.
this is something.
M4, raise your hand, M4. Guys, who's paying balls back with no caps? You're not children. Get this together. There's one with no caps. Somebody has a cap.
Oh, yes.
Who else is ready? because you have it on the solution.
That point.
You guys need to begin or your solutions will evaporate. You need to begin. Analysis ready for M4.
We already know
Follow your data tables, follow your instructions very clearly. Make sure everybody's watching the instructions. You can make the number bigger. So you or the bottom.